So far, we have seen how do we measure the spatial scale of the universe, which is simply 1 over a Hubble constant. What about its temporal scale? What's the age of the universe? It turns out that we actually can't measure the age of the universe directly. However, what we can do is measure lower limits to the ages of oldest things we can find. And then presumably the age of the universe is just a little more than that. Several different possibilities exist. The first one is the globular star clusters. These are believed to be formed over a very short time interval in the early universe, and all stars in them have essentially the same age. Understanding the ages of star clusters or stellar populations is the basic fundamental thing in stellar evolution theory. So in principle, we understand how that changes by looking at their color magnitude diagrams. The second kind of thing that we can look at are white dwarfs. Again, these are inert incandescent cores of low-mass stars that are now slowly cooling down. The cooling theory is fairly well understood, and by observing apparent luminosity function of white dwarf stars, we can estimate how old are the oldest ones of them. Another thing we can do is estimate the age of the heavy elements created in stars. Very high mass elements would tend to be radioactively unstable. And if we can find long-lived isotopes of some of those elements and measure the relative abundances, we can estimate the age of those elements, which presumably came from supernova explosions in some of the very first stars. This is very similar to the carbon dating that's often used on planet Earth. That is somewhat model dependent because it depends when the supernovae were exploding, but the upper limit of that would again give the lower limit to the age of the universe. And finally, we could model stellar populations in a similar way that we model star clusters, but that turns out to be much more complicated, and it's really not used to constrain the age of the universe. The fundamental measurement here is estimating the ages of globular clusters, which are almost as old as our galaxy itself. This is based on a well-established and well-tested theory of stellar evolution, which predicts so-called isochrones, which is color magnitude diagrams and the paths that main sequence and a giant branch will have at any given time. They look like this. The main sequence turnoff moves to ever lower masses, lower luminosities as time goes on, and then stars ascend the giant branch. So by measuring where the main sequence turnoff is and where the giant branch is, we can fit the models and find out how old the cluster is. Likewise, the difference between the turnoff and the position of the horizontal branch is another age indicator. The isochrones will depend slightly on the chemical composition of stars in the cluster. So there are many uncertainties in those estimates, but the biggest one of them all is the uncertainty in the distance to the globular clusters. Stellar evolution models are pretty good, but in detail, there's still some minor uncertainties that need to be resolved. The exact effects of the different abundances of chemical elements and diffusion from stellar cores in which they're made towards the surface and so on. Those also contribute to the uncertainty in the estimate of ages of globular clusters. Nevertheless, measuring ages of globular clusters was probably one of the more reliable cosmological measurements for many years, certainly more so than any other cosmological parameters until the 1990s. The key point here was to calibrate exactly where the main sequences are. And this became possible only after the Hipparcos satellite measured the actual parallaxes and distances to some metal poor stars, which define the metal poor main sequence that can be then applied to globular star clusters. Different groups have done that, and typically the results they get are the ages of globular clusters are of the order of 12 to 13 billion years, which is very close to what we now know is the actual age of the universe of about 13.7 billion years. Here is a probability distribution of globular cluster ages that take into account all of the sources of uncertainty and so on. Clusters could have different ages, and they probably do, so that will contribute to the spread as well. So the peak of this distribution is indeed where it should be, a little more than 13 gigayears ago, which allowed for a few hundred million years for galaxy and clusters to form. Of course, there are no clusters older than the universe itself. The fact that the distribution has a high end tail is simply indicative of the errors in age estimates. The next method is estimating the ages of white dwarfs. They are fairly well understood and they're cooling in a very orderly fashion. So the faintest white dwarfs that we can find are probably the coolest, the ones that have been cooling for the longest period of time, and they can then constrain the age of the cluster or galactic disk in which they're found. Again, theory is fairly well understood in overall sense, but there are still details that need to be ironed out. Probably the best way to do this is in star clusters, where again we know that population of white dwarfs all have the same age, and because they're really faint and clusters are crowded, we need Hubble Space Telescope to do this. Here is an example of the first measurement of this kind. In the upper right, you see a little segment of the main sequence. In the center is the white dwarf cooling sequence, and you can see it stops at some point. Those are the oldest and the coolest white dwarfs in the cluster, and their position determines the age. So this method produced results which are perfectly consistent with those from main sequence isochrone fitting, and that's very different physics, so it's very encouraging. Here is the observed luminosity function of white dwarfs in this particular cluster, meaning their distribution of their luminosities. And you can see that there is a fairly sharp cutoff at the faint end, which is indicative what the age really is. An entirely different approach uses ages of chemical elements. Heavy chemical elements that must have been produced in supernova explosions of, say, first supernovae often have unstable isotopes, and their radioactive decay can be used to age date the elements themselves. Because the age of the universe is about 13 billion years, you need radioactive decays that are commensurate with it, again measured in billions of years. There are such isotopes like thorium and uranium. There is also rhenium and osmium and a few others. And so you need something that has a radioactive half-life decay time of flight time. But that unfortunately also means that it will be really hard to measure in the laboratory what that half-life decay time is. So doing this for a variety of different isotopes then provides the estimate of the age of the oldest supernova explosions, oldest chemical elements in our galaxy. The abundances of these elements are done by very high resolution, high signal-to-noise spectroscopy of oldest stars we can find. The lines are very subtle and the measurements are very hard. Nevertheless, they've been done over years and results are shown. So for one particular star shown here, here are ratios of several isotopes that are being used to estimate the age of the elements that made the star. And the average of it is remarkably close to what we now know is the actual age of the universe. And it's also essentially the same as the ages measured for globular clusters and for white dwarfs. This is just one star. Doing this for many stars improves the result. And so to recap, we have now a fairly good idea of what the age of the universe is, or at least the lower limit to it, using several completely different methods, which rely on different physics, different assumptions, and different measurements, and they all agree. It's because of that that we think we got it right. Moreover, this is also in perfect agreement with age of the universe deduced from measurement of other cosmological parameters, to which we'll come later. Next time, we will address the question of, is the universe actually expanding? You think we would have probably figured this one out by now, but it's good to be sure.